This is the next session in the course of Artificial Intelligence. So, we will talk about genetic programming in this particular session. So, genetic programming is a variant of the genetic algorithms which we studied in the previous session, and these genetic programming actually is used to find genetic programs or to generate genetic programs for a particular task at hand. So, this was actually suggested by Koza. So, this was in 1991-92. You will find books that he has written on this genetic programming, where he gives the concept as well as a number of applications where it has basically been used. So, here the structures which are being adapted are segments of computer programs. So, you have different segments of computer programs, and these segments of computer programs are grown so that you get more and more computer programs of various sizes and complexity as you go on working on the genetic program. And the fitness generally of a program is measured by its ability to solve a set of tasks. So, you see for each of those tasks whether it is able to solve the task or not, and that information is used in the fitness measure. And just like in genetic algorithms, we are going to use crossover and mutation on program subtrees. So, generally it is in the form of a tree, each of the program segments that you are going to find, or each string is in the form of a program subtree. So, we will see how this actually works. So, basically you are searching in a space of computer programs for solving a particular problem, and this computer program can be of various types, various complexities, and each of them is evaluated, and each computer program will consist of some functions, some terminal symbols, etc., all put together to solve the problem. And the search is of course random. You are just putting pieces of random information together and seeing how well it solves the problem. But as you go on doing, it's not really random, because you are trying to use information to make it more like a focused search after some time. Same as in the genetic algorithm. So, genetic algorithm also starts off as a random search, but later on it becomes more focused towards the better fit strings. So, what you are trying to learn is a program for carrying out a particular task. So, it starts off with the initial population of randomly generated programs. So, you have program pieces which are put together. So, it could be the functions that we talk about could be things like standard arithmetic operators or other programming operations, mathematical functions, etc. You can also have logical functions, you may have some domain specific functions also put into it. So, all these together will form the functions that you are going to use. And what would be the terminal symbols that you are using? They will be symbols of various types. It may be Boolean, it may be integer, floating values, vector, symbolic, multi-valued, may even be matrices and things. So, what happens is once you initialize, you will be moving from one population to another population, and you will be breeding a lot of computer programs for solving a particular task. And from these thousands of computer programs which are being generated, you find the best possible one to solve the problem that you are actually working on, because you will have a number of instances in which you are seeing what the output is supposed to be. and if the output is correct for most of them, it means that computer program actually solves the problem that you are looking for. So this production of new programs is because of the genetic operators that you are using. So it's just like in the genetic algorithms, we talk about getting a new population of strings for solving the problem. Here we get a new population of computer programs. So you find more and more computer programs which are being generated. And of course, you are using things like crossover and mutation. But here, because you are talking about the subtrees which are being used, you got to see how actually you carry out the crossover and mutation. Of course, selection is done in the same way as it is done in the genetic algorithm. Once you find the fitness. Of course, depending on the problem domain, you can have different fitness measures. So if it does well on all the fitness tasks, so you are going to give it a number of tasks, and if it does well on all those tasks or most of the tasks, then you say yes, it is solving the problem that you are looking at. Okay. So there are 6 components you have to consider, a set of structures. So you start off with some structures which keep undergoing transformation by using genetic operators and coming up with new computer programs. And of course you start off with the initial structures suited to the problem domain, and each of these structures is evaluated by using a fitness measure which is domain dependent, and you have a set of genetic operators to transform these structures. And parameters state description that describe members of each generation. In other words, how do you describe each of these strings in each generation and look at it as a computer program for solving a problem. And finally, you have the termination conditions which will tell you when to stop this procedure and say, okay, we have found the computer program we are looking for. So you have hierarchically organized program modules, which means they are trees, subtrees. Okay, for example, one string may be one tree and the other string may be another tree. And how do you carry out crossover on this, mutation on this? That's what we are going to see. So, like we saw in the Lisp program, Lisp program basically is for list processing. So, it's in the form of a list, and this list actually corresponds to a tree. Okay, so it can be used for trees, and each of these program segments is known as a S expression, what is used in the Lisp, and that is exactly what is used to represent these trees in genetic programming. So genetic operators are used to manipulate these S expressions. So the S expressions can be put as, like I said, as trees, and these trees can be combined together in some ways to get new trees. So first of all, before we start the genetic program, we need to see what are the functions that we need to use, what are the terminals that we are going to use. So obviously, you are using functions and you are using terminal symbols. So like we said, you have F, the set of functions, and T is the set of terminal values required for the domain. So what are the functions that we could use? The simplest could be just plus, minus, multiplication and division, right? You could also have things like square root or square, could have sine, cos, so many things. Even matrix operations are possible. So all these together, or it could be something else depending on the particular domain in which you are working. So all these will form the functions that you are going to represent, and T is the set of terminal symbols, which may be a symbol which is a integer, it could be real, it could be matrices or other expressions. And whatever symbols you are using in T must be closed under the functions defined in F, right. So this is, there is some connection between the F and the T. So what you do is you randomly start the initial programs which you are going to generate, okay. So let us see how this actually is done. So suppose we just talk about a domain where we have just plus, minus, multiplication, division, maybe sine, cos, etc. So what we do is if you choose a random element in T, okay, for example, maybe some A, okay, then it will become a degenerate tree with just one single node, because you have reached a terminal symbol, so you don't go any further than that. But if you start with an element in F, for example, suppose you start with plus, so plus actually should have two potential children, right. So it could be A and B, because you may be doing plus A plus B, right. So you need to have two children to that. So suppose the initial thing you are going to start with, the function you are going to start with multiplication, and then it will have two children, right. So it's something like this. This is your say the first symbol plus you are going to start with, right. So it has to have two children. So you see what you are going to put here and what you are going to put here. Now what you take here, suppose it's randomly multiplication sign, so you will get the multiplication there, and you will because it's a multiplication you will get two children, and suppose on the other side you have one terminal symbol, so for example 6. So this doesn't go any further, and this has two children, so again you find the two children. If both of them are terminal symbols, then this is your program structure, okay. So your first string is going to consist of this subtree basically, which is generated at random, we can see, right. Okay. So now once we generate a population, so we saw how we generated one string, okay, but we can actually generate a number of strings in this way, and once we generate these strings, each of the strings need to be evaluated. So how do you evaluate it? You usually have a table which will tell you under these conditions this is the output that we are expecting, right. So it usually consists of a set of tasks the evolved programs must address. So how well the function works on all these tasks have to be taken to calculate the fitness value. So one way of finding it is that you see find the difference between what the program has produced and the result, right, and the result which you get from what is given to you. And so this would be like a fitness score, the error that you're going to get, right. And if you take this error and across a number of tasks, you can add up all these errors, okay, and that may give you the fitness value. And if you divide by the by the total sum of possible errors, you will get it between 0 and 1. You can also use other things in your fitness. For example, the size of the program. Obviously, you would like a program of a smaller size, okay, which does the same thing, rather than have a longer program. So you can use that also in your fitness. That means you are trying to reward smaller, more parsimonious programs which do the same thing. Okay, so you can add that also into your fitness. So the fitness measure is up to the user to see what is the best fitness that he needs to use over there. Okay. So let us look at the genetic operators that you are going to use on this. Reproduction, we know the reproduction is the same as the reproduction we learnt in genetic operators, but let us look at the crossover. Crossover exchanges subtrees. Okay, for example, if we have two trees like this, right? At random you choose one point in this subtree and you can choose one point in this subtree, and you can decide you are going to exchange these two subtrees. Okay, in this tree you have chosen one point, in this tree you have chosen one point, and the subtrees which result from this are exchanged. Okay, so you can maybe put this cause here and you can put this part of the thing over here. Then you get two new strings like this. You can also do this in the same tree. So for example, in this tree, you can take this as one you are going to exchange, and maybe this is another cutoff point. Maybe this is one cutoff point, this is another cutoff point, and you can exchange this part and this part, right? So this is how you can carry out crossover in this. And you can see that you can get different strings by carrying crossover. Okay. You can also choose the root of the program as the crossover point. Okay, and you can exchange. You can change the root of the two programs also. That's also possible. And how do you do mutation? Mutation is that you simply take some terminal symbols and replace it by randomly other functions or terminal symbols. Okay. So for example, you can take, say, this is a terminal symbol, and this is a you can take away this terminal symbol, and maybe your terminal symbols vary between, say, 1 and 10, and you can replace this with some other terminal symbol, okay, or with some other function also. So if you replace it by a function, then again you need to get two children for that, and you can select them at random, or you can change it to another terminal symbol. So that's how the mutation will actually take place here. Okay. So the permutation transform, similar to the inversion, also works on single program exchanging terminal symbols or subtrees. So you can exchange this and this. Okay, you can exchange 10 and 6, put 6 here and 10 here, that type of thing. Or you can exchange functions also. You can say that you put your sine here and cos here or whatever. Okay, so anything is possible when you come to mutation. You can do anything that is legally possible in your program. So the GP paradigm parallels nature in that the evolution of new programs keeps on going, right? And it keeps on breeding more and more programs, and then you set some termination condition at some point in time to stop this. So one termination condition you can think of is that it works okay in all the tasks that you have given. So if it works on all the tasks, it means that is a proper program to carry out this task. So to understand this better, we will look at one example over here. Okay, so there are many complicated examples given, but this is actually one of the simplest examples that is given. So let us look on this. So this pertains to Kepler's third law of planetary motion, okay, which is a relationship between the P and A. Okay, A is the distance of the planet from the sun, and this is known as the orbital period of the particular satellite. Okay, the period, the revolution or the rotation of the satellite which we are talking about. So the function actually, if you look at Kepler's third law, is actually p square is equal to c times a cubed. In other words, c is constant. So you can say that p square is proportional to sort of a cubed. So this is a relationship between p and a, and we are trying to find this. So suppose we assume that p is expressed in units of earth years. Okay, so that is how you express p, and a is expressed in units of earth's average distance from the sun. Okay, so these are the two things, and we are what we are going to say here, we can say that p is equal to square root of a into a, and this is the program we are trying to evolve from this, right. We are trying to find a relationship between p and a. Okay, so that's the basic idea here. Okay, so this is what we are going to try to get. Okay, so this is the target program which we are looking at over here. Okay, and so what we need is, we have a single terminal symbol here which is a. Okay, so a is the terminal symbol we are going to use, and let's say that the set of function is just plus minus multiplication, division, square and square root, right. So this is the set of functions that we are going to use. So you randomly generate the initial population. So let's say this is the initial population we have generated, right, and we are given this particular table over here. Okay, so it tells you for the various planets, for these various planets, for different for a value of a, what is the p that we are getting over here. Okay, so so this gives a set of fitness cases with planetary data where a is Earth's axis of orbit, right, and p is the units of Earth years. So we have this table, so we can make use of this table, and since we are getting a relationship between p and a, right. So we can see here in this particular case, okay, in all those 6 cases that we have seen, in how many of those cases do you get the value? So you are going to see whether it comes within 20% of this value. If it comes within 20% of this value, you are assuming that it's solving the value you are looking for. So what you do is, you check for all these 6 cases, in how many cases is the program we are using solving the problem. So that is the fitness that we have put over here. So it means that this one is giving the correct result only in one case, the second one is giving the correct result in 3 cases, and the third one is not giving a correct result in any of the cases. So the number of cases in which it gives the correct result is taken as the fitness of that string. Okay. And you can also generate more strings if you require, like as many strings as you want, you can generate over here. Okay, so these are the original initial population that we have generated, right. So this gives you the string 1, the string 2 and the string 3. So these are the 3 strings that we have generated over here, and we are making use of this, and the fitness measure is a function of the data points we want to explain. We define fitness as a number of outputs of the program that come within 20% of the correct output values. So we create the fitness measure for the 3 programs that we have, right, like we have done over here. You can add more into the initial population. For each of them you can find the fitness values that you are looking for, and once you get these fitness values, you can use some method of selection, right? Just like we use in the genetic algorithm, it could be either roulette wheel selection, you can use deterministic selection, or you can use any of those 5 or 6 different selection measures that we used. And then you can use the crossover and mutation that we know, and you can get that next generation of programs, right? And on that you can use again use a method of selection, method of crossover mutation, etc. And what would be the termination criteria here, since we are taking the fitness to be the fitness of the string in in 6 cases. If the fitness comes to 6, or if the fitness you are getting is close to 6, or if it becomes 6, which means in all the 6 cases, okay, in all the 6 cases that we have used here, it's coming within 20% of P, with the actual P. Then you can say that you have reached the termination criteria and you can stop at that particular point in time, and the string which gives you the best fitness can be the one that you are going to take as the program. So this is the way you generate the program. It's also possible that you can run this for a large number of iterations, maybe like 500 iterations or 1000 iterations, and then you can see the one which gives you the best fitness, and you can take that as maybe the one which gives you the best fitness with the smallest length. Okay, so that is the number of bits that we have in this. If that is also reduced and it gives the highest possible fitness, that would be the one that you are going to take. So in this way you could also try to see, for example, if you take electrical networks, you can try to derive the relationship between the voltage and current, right, to see the resistance values, right. So you can also do that, and in this way there are I mean, these are all simple things that we are talking about. You can also do more complicated programs can also be developed by using this genetic programming. Those who are really interested in this direction can look up Koza's book, because he has actually, it's just a book called Genetic Programming, somewhere in 1991, which gives you a lot of applications where you could use. He's also spoken about implementation and how you can implement this genetic programming using the S expressions in Lisp. So this is the general background for genetic programming. We'll not go into much details about it. So we'll stop this session at this point.